Welcome back, everyone. For the following compound, number 1, draw the appropriate Lewis structure. Number 2, identify the type of orbital used by every carbon to make chemical bonds and estimate the bond angles. We're given the structure of acetonitrile. First of all, if we want to draw an appropriate Lewis structure, we have to calculate the number of valence electrons in the given structure. We have 2 carbon atoms in the structure, 3 hydrogens, and 1 nitrogen. Carbon has 4 valence electrons because it belongs to group 4a. Hydrogen has 1 valence electron because it belongs to the group 1a. And finally, nitrogen has 5 valence electrons because it is within the group 5a in the periodic table. So if we have 2 carbon atoms, we're going to multiply 2 by 4. We're going to add 3 hydrogen atoms. And specifically, we want to multiply 3 by 1. That will give us the total number of valence electrons contributed by hydrogen. And then we are going to add 5 valence electrons from nitrogen. So the number of valence electrons would be 16 because we have 8 plus 8. Now that we have the total number of valence electrons, we want to assign our central atom. And in some cases, we will not have any central atoms, but we have to recall that central atoms tend to be less electronegative. So if we start with our nitrile group, we are going to draw our carbon-nitrogen bond, and we will make sure that nitrogen is terminal because it's more electronegative, meaning the remaining carbon will be bonded to carbon, and the 3 hydrogen atoms will be bonded to that carbon. Right? Because whenever we are dealing with Lewis structures in organic chemistry, we can just read those condensed structures from left to right. And that's why we assigned 3 hydrogen atoms bonded to the first carbon, followed by the carbon-nitrogen bond. Well done, we have our bonds. We notice that there are 2 central carbon atoms. And now our next step is to actually satisfy the octet rule for the terminal atoms. In this case, none of the hydrogen atoms needs an octet because hydrogen follows the duet rule. So we want to make sure that we satisfy the octet rule for the terminal nitrogen. It has 2 electrons from the carbon-nitrogen bond. So we're going to add 3 lone pairs on nitrogen. And now, if we calculate the total number of electrons assigned, we have 1, 2, 3, 4, 5 bonds. That gives us 10 electrons, plus 6 electrons coming from the lone pairs of nitrogen. And that gives us 16, which is exactly the number that we had to get, right? This is the total number of valence electrons that we must end up with. So there are no lone pairs that should be added to carbon. But there is a problem. Carbon does not have an octet, so we're going to use one of the lone pairs of nitrogen to introduce a double bond. But because it still doesn't have an octet, we're going to use another lone pair and form a triple bond. So now both nitrogen and carbon have octet. And that means we are ready to conclude that the final Lewis structure will correspond to the methyl group, so 3 carbon-hydrogen bonds. Then we're going to bond carbon to that first carbon atom. Then we will have a triple bond, nitrogen with a lone pair. Of course, we can apply the formal charge formula to verify that the formal charge for each atom is indeed 0, but it's sufficient to notice that carbon has 4 bonds in each case, so each carbon has a formal 0 charge. Nitrogen must have a formal charge of 0 whenever it has 3 bonds in a lone pair. So everything makes sense, and we got the required Lewis structure. Now, for the second part of this problem, we want to identify the type of orbital used by every carbon to make chemical bonds and estimate the bond angles. So let's go ahead and do that. We can just redraw our structure. And of course, first of all, let's recall the types of hybridization. So sp corresponds to 2 electron regions and an angle of 180 degrees. Whenever it comes to sp2, 3 electron regions, a bond angle of 120 degrees. sp3, 4 electron regions, 109.5 degrees. The number of electron regions is just obtained from the sum of the superscripts. Sp stands for S1P1. So for example, 1 plus 1 gives us 2 electron regions, so it's very easy to memorize this. So now when we consider every carbon atom, we notice that within the methyl group, we have 4 electron regions because we have 4 carbon-hydrogen bonds. And that means we have an sp3 hybridized carbon atom. On the other hand, when we consider our nitrile group, there are 2 electron regions, 1 single bond and 1 triple bond. So that means the carbon atom from the nitrile group is sp hybridized. Well done. Knowing this information, we can start analyzing our structure. Starting with the carbon atom from the methyl group, let's conclude everything that we know about it. Every bond angle will be equivalent to 109.5 degrees. So we can say that, first of all, hydrogen, carbon, hydrogen bond, every of them, HCH, that bond angle will be equal to 109.5 degrees. In addition to that, we have hydrogen-carbon bond. So we are going to say that hydrogen-carbon bond will also correspond to the same tetrahedral bond angle. All of the bonds, including CH and CC, they will all be within the sp3 orbital, because an sp3 hybridized carbon atom produces 4 sp3 orbitals. It's also important to understand that each bond is a sigma bond, so CH sigma bond and CC sigma bond, they all correspond to an sp3 orbital. And we are done with the analysis for one of our carbon atoms. We are ready to move on to the next one from the nitrile group. We are going to consider our bond angles. And of course, just as we said, because the hybridization is sp, we are first of all going to say that CCN, that bond angle is linear, right? So let's go ahead and state that CCN bond angle is 180 degrees. Also, we have to recall that only sigma bonds will correspond to sp orbitals. So we are going to state that Cn sigma bond and Cc sigma bond, they will correspond to sp orbitals. And now, of course, we have to recall that a triple bond consists of 2 pi bonds. And these 2 pi bonds, specifically the carbon-nitrogen pi bonds, will correspond to p orbitals which are not hybridized. And that's really important to understand because we have an sp hybridized carbon, so there will be two p orbitals which are not hybridized. Well done, so that'll be our final answer. We got the Lewis structure, we got the required two orbitals, and the bond angles. Thank you for watching, and I hope to see you in the next video.